Okay, like Randy Quaid said in Independence Day, hello boys, I'm back, and so you've got to put up with me again. I like to blame, attribute or maybe blame my papers on the works of others. So yesterday I was able to blame what I did on Holt and Arp. The one I just gave I could blame or attribute to the work of Duncan. This one I'm going to blame on Bob the Hilster because I had never heard of pushing gravity until the first conference that we had down in Florida in 2015. He had a couple of papers on pushing gravity. I said, where did this come from? And so I looked it up and said, hey, this is interesting stuff. So I'll blame this one on Bob.
You're welcome.
He's a mad scientist anyway. Actually, though, the real people to blame for this go back to 1690. Fatio was the first one to come up with this, and he sent it in 1731 to the Paris Academy of Science. LeSage got a hold of it in 1748, and they had a theory that gravity is a pushing force that involves shadowing of omnidirectional particles that impinge on all matter so as to appear as an attractive phenomenon. So let's look at a special case of a large distance between spheres. Mathematically model gravity as a pushing force with shadowing and include the possibility of acting throughout the shadowed corridor of the sphere with an attenuation effects to suggest a possible alignment with one of the known effects of gravity. Gravity is inversely proportional to the square of the distance between the sphere's centers. So I decided to look at the LeSage, the Fatio LeSage math to see if I can come up with this inverse square relationship. This does lend some credence to the theories of Fatio and LeSage and has been supported by many dissident physicists, including members of the gravity group, which, are they still together? No, but there was a gravity, about 4 years ago, there was a gravity group with Bob and a few others in there, and they had the paper. So again, I can attribute this work to what I learned back in 2015 at the first conference. These are the diagrams you typically see. Up here you see the two spheres, you see all these little particles going back and forth, and it doesn't show real well, but they're less dense in between the two spheres. And they also got little holes, so these look like wiffle balls, because they do postulate that the spheres can pass through in some cases. But there is some shadowing, which is shown below. So despite repeated rejection, this theory has survived over 300 years, even been reviewed by dissident physicists as mainstream physicists continue to struggle with an explanation for gravity. They come up with gravity waves or gravitons. They propose in connection with gravity as a four-dimensional wave phenomenon. I don't know what the fourth dimension is, except I don't think time is a dimension like the other ones. Shadowing is inherent to explanations of gravity as a pushing force. If a force is transmitted to a body from something pushing on it from all directions, the body would remain stationary. That's this one here. So we just got this sphere sitting alone and everything's pushing on it equally, and it's like a balloon with equal air pressure. If a second body is brought close to the first one, part of the impinging force on body one would be blocked out and cause a net push towards body two. So body two gets in the way, it blocks out this arrow and a few of the other arrows here, so all of a sudden, these three arrows here don't have anything, or well, at least this arrow here doesn't have anything to offset it, so one would start getting pushed towards two. And if I showed arrows on number two, you would see that this arrow here on number two is not offset on this side because of the shadow of number one, so number two would start approaching number one. That results in what would appear to be an observer, to be an attraction between the two bodies. So push, pull, they can be equivalent. At least they can appear to be. So I decided to look at some geometry. So I got my two spheres separated by a distance d. There's d down here. Between centers with radii r, the bigger capital R for the big one, small r for the small one. The mass is 4 pi capital rho, which looks like a p, for the big one, 4 pi small rho for the little one. The gray arrows here on the outside, they show are omnidirectional pushing forces, whether they're particles, waves, or combinations, and they're the ones, they remain unshadowed except for this little part here, which is, as you can see, between the two spheres, that this part here is blocked out on this side, so you do have a net push over this 2 theta on the small sphere. You have a net push over this 2 phi on the larger sphere because of the blockage between the two. The net pushing force results from area over which the pushing forces are not offset by equal and opposite pushing forces diametrically opposed. That is, the cones, again, this is a two-dimensional picture, but they're spheres, so this is really a cone with a solid angle type of thing. Not offset by equally and opposite pushing forces diametrically opposed. That is, the cones of radius r, bigger sphere, and small r, little sphere, with solid angles phi here on the big sphere, and theta on the small sphere. When far apart, d much greater than r, and since capital R is bigger than small r, d is also much greater than small r, we can simplify the geometry. Any exaggeration here is for clarity. Essentially, this triangle here, when the d is real large, is essentially a right triangle, the same over here. And so I can do some simple calculations just using Pythagorean. And what they both end up with is that the cosine of theta and the cosine of phi end up being approximated as the separation distance over the separation distance. So it ends up to be 1. So that'll simplify some stuff. The net pushing force on each sphere is proportional to the cross-sectional area subtended by the cones of the two different radii. That's the sine functions here, pi r sine phi squared, sine theta squared, effectively acting along a vector parallel to that between the centers of the two spheres. With the separation distance much greater than the radii, each of these simplifies to pi times the product of the two radii over the separation distance, that ratio squared. Each sphere has inertia proportional to mass, resisting each pushing force. So if I accelerate each sphere, it will be proportional to the exerted force divided by the mass, such that the accelerations become as follows. So the larger sphere, here's the force, and here's the mass. So this is the acceleration on the larger sphere. The smaller sphere, here's the force, same force, but slightly different mass. It has small rho, small r, so this is the acceleration on the smaller force. And lo and behold, both are proportional to the inverse square of the distance. They're both proportional to 1 over d squared. Now, strictly speaking, these accelerations need to be multiplied by the change in momentum per unit area from the impinging particles. So I have to, just to be dimensionally correct, I throw in the term delta here, which actually has units of kilograms per meters per second squared. The first part of it, kilograms per meter per second squared, represents the change in momentum, kilograms per meters per second, coming from the impinging particles, sort of like the ram force that Duncan talked about earlier. The second is the inverse of the impingement area, the surface area. So the accelerations are more actually written with the delta term in there. So the same accelerations as before, now I've put the delta in each one of them. Dimensionally, each acceleration now has the correct units of meters per second squared. So that's just to make things a little cleaner here. Now within the spheres, so far I've only considered the spheres as solids, impenetrable solids. That is, the pushing force acts only at the surface. Fatio and LeSage and the gravity group and others who espouse gravity as a pushing force usually assume that it has an effect going throughout the target, that is, as it passes through the sphere. Let's consider the pushing force acting not only just at the cross-sectional area of impingement, but throughout a cylinder as it hits the surface area in a small circle. Look at as it passes through in that. Extending through the sphere whose axis parallels the vector that connects the centers of the two spheres. Now I'm going to include the linear distance through each sphere that the particles theoretically pass, effectively multiplying the previous results by the diameter to obtain the following accelerations, because it acts throughout the diameter, so twice the radius. So the larger sphere acceleration now has an additional distance of 2 capital R, the smaller sphere 2 small r. So the accelerations become these formulas here. Again, they're the same except the r's and the rho's switch. The dependence on the inverse square of the separation distance remains evident, but now without the inverse dependence on the radius of the sphere itself. If you remember previously, there was an additional distance term in the denominator. There was a capital R in the first one and a small r in the second one. These terms in red have now disappeared because I've interacted them over the entire sphere. Dependence on the square of the radius of the outer sphere, of the other sphere, that is the one that shadows remain. So I still have my d squared dependence, which is what I wanted. I don't have a distance cube type of thing, which I would have had if I still had the radial distances in the denominator. Proponents of gravity as a pushing force sometimes assume that in addition to the shadow effect, the force itself may be somewhat attenuated as it passes through the sphere. There's some sort of interaction that may actually either slow down the particles or absorb some of the particles, and that's really where the shadowing comes in, because not all the particles that go in go out as they come into those angles. Attenuation over a linear distance x is usually modeled as an exponential decrease, 1 over e to the mu x. Mu is some form of attenuation coefficient. It's usually some function of the density. Here I don't specify the exact functions, just a capital F of capital rho for the larger sphere and small f of small rho for the smaller. Now if I throw this into the acceleration as another multiplier, I end up getting, they're in the denominator, so I have what I had before, 3r squared, the delta 2 rho d squared, and now in the denominator I have this exponential term, which since it's positive is going to be greater than 1, and so it'll show that the acceleration has decreased because of the interaction. And now we're just forming for the smaller sphere. Once again, the dependence on the inverse square of the separation distance is evident. I still have d squared in the denominator, but now I have some reduction due to attenuation. I have this exponential attenuation form, which I put in the numerator, which will have a minus sign on it. A ratio of accelerations larger to smaller on the two spheres yields the following. So here I'm taking the ratio of the larger to the smaller sphere's acceleration. So I get that it's the ratio, it's proportional, well that's actually equal because I'm doing the ratio of the two radii squared, the ratio of the densities, and it has the exponential term, which is 2 times the difference between the product of the radii and the mu function. Again, the attenuation function, which instead of writing the mu here, I've written as f of rho and f of capital rho. Again, r is greater than r, capital R is greater than small r, so the first term likely will dominate. Unless capital P is much greater than rho. For example, comparing a neutron star to a typical star. So then that could dominate. Or f of rho is greater than small f of small rho. What I'm trying to show here is that the acceleration on the larger sphere is always going to be smaller than the acceleration on the smaller sphere, because like the Earth and Moon, the Earth's gravity on the Moon is greater than the Moon's effect on the Earth. And it tends to fall out from here. Again, the smaller sphere, the larger sphere, the ratio, this is less than 1. Unless the densities are grossly different, this term is probably around 1. And unless the, again, function of the density, if the densities again are fairly comparable, then these terms are f of rho and capital F of rho are probably similar, and you'll end up with a somewhat negative value here, so that becomes e to the minus something because r is bigger than r. So it shows that the ratio should be less than 1, which is what we expect. Again, the acceleration on the larger sphere is less than the acceleration on the smaller sphere. The effect of the larger sphere feels less acceleration than the smaller sphere. Acceleration on the larger sphere should most often be smaller, should be less than on the smaller, implying less movement towards their mutual barycenter on the part of the larger sphere. And that's consistent with observation. I mean, the Earth and Moon, they rotate about a barycenter that's about 1,000 kilometers below the surface of the Earth. So it's kind of a wobbly thing, and that basically the Moon has been drawn a lot more closer to the Earth than the Earth has been drawn to the Moon. So in summary, at least for large distances between spheres, a mathematical model that assumes gravity to be a pushing force, with shadowing and including possible attenuation throughout the shadowed corridor of the sphere, suggests a possible alignment with one of the known effects of gravity. It's an inverse proportionality to the square of the distance between the sphere's centers. I've hopefully lent some credence to the theories first proposed by Fatio and LeSage and since supported by many dissident physicists. After I wrote this paper, I found a really interesting derivation of Newton's gravitational equation from LeSage's attenuation concept. And this addressed not only the inverse proportionality to the distance, but also the direct proportionality to the product of the masses. This is a reference for that, and if you're interested in this and you want to do more than I did, which was also bring the masses directly in there. I mean, I have the masses sort of in there in terms of the densities, but these guys were able to get the mass, the product of the masses in the numerator, so they were able to show that pushing gravity can yield directly Newton's gravitational formula. And the crackpot is done.
Questions? No?
I'll get up. Well, at least I need to say thank you, right? Thank you, Ray, for doing the analysis. I've done all of that analysis myself in a different way. An appendix in my book, Gravity is Not Free, I discuss R squared. And my general conclusion is, yeah, it generally meets R squared, but R squared itself becomes an approximation because the equation I developed has terms which adds other things that Newton doesn't have. The second comment is about Mingst and Stowe. In the book Pushing Gravity, there's a chapter by them, I believe, and they show that development of Newton's equation. So if you really want a good overview of a lot of different people who have reviewed Pushing Gravity, that book has a lot of information, including a lot of detail on Bejarano's experiments in the 1920s, where he tried to prove that pushing gravity was valid. So anyway, other than that, I have to agree with what you said. Very well done, Ray. I appreciate it.
Any other questions, comments? No? Okay, thank you very much.